The name of the video is Appendix Constant on Infinitesimal. Okay, so suppose that we have the component, the magnitude of a certain electrostatic field E. Let's catch it in this fashion here. This is E as a function of a coordinate x, for example. This is the origin. Suppose that this function looks at something like this. Etc. Suppose that we want to integrate this quantity, so we know that numerically, for instance, we can proceed by binning this curve. And so we can bin it in a couple of different ways. For example, we could choose this point here, if I start to bin it from this point here, for example. So then I can make a bin which is constant for a certain length here, until this point here. Okay? And let's call this quantity delta x. So then we go further up here to the next bin, and we keep it constant for the same quantity delta x, and so on and so forth. And we can continue to eventually recreate the entire structure. So then we do just the base times the height, and we obtain the area of this under this curve. Okay, it's a numerical approach to compute the area, the integral that is under this curve E. Of course, you could also bin it in a different fashion. So you could bin it in such a way to start from the center here of the point. So the bin is centered around this point in this fashion like this. It's another approach that we can, of course, follow. And so then here we would go to the center again, and we keep the same bin size all the time, which again is at delta x, the distance between each of these points. So eventually, if you want to get a more and more accurate result, you want to go in the limit that delta x is very small. So eventually, we make it just a dx, okay? So in this case, suppose that I have a value of the electrostatic field here. When I integrate, I keep it constant throughout the bin, and then I move to the next value and keep it constant. All right, so that's the way we integrate. So we can keep it constant over a small quantity, which is our dx. So if you make a comparison with the problem of the infinite line revisited, which was the revisited square, so at some point we had something like this. There was a circle. This is the origin here. And we had something like this. Let's do two of them back to back. This angle was d bar phi. And what we hypothesized there is that the electrostatic field E bar phi, which we chose to start at this point here, we said that it was constant, this field, we said that it was constant on each and every point of this line here. Okay, that's what we said. We said it was constant on each and every point. So similarly, if I pick now this new point, perhaps here I have a field which goes in this direction and is much longer. So this is E bar phi at this point. Let's call this point, for example, P1. And this point we call it P, capital P2, so capital P1 and capital P2. So E bar phi at point capital P1 is here, and this is the field E bar phi at point capital P2. In general, at point capital P2, E bar phi can be different than a capital P1, but again, over an infinitesimal angle, so this is also d bar phi, same as here, we consider it to be exactly the same. So as before, these were our two equal angles, okay, infinitesimally small. All right, so it's the same kind of concept we have done here. That's why we could assume to be constant there. This doesn't mean, again, that the field at point capital P1 is the same as at point 2. Also note that we could have chosen as the point, for example, instead of the edge of this wedge, we could have chosen the center. It would have been the same thing. So we could have chosen this to be my point capital P2, and therefore having our field starting from there instead, okay, or from here. It would have been exactly the same thing. We can do the same argument. It's exactly like the binning, center binning or offset binning we have seen here. All right, so that's the similarity between these two concepts, which I think is quite important. But let's try to answer the question, which is, okay, so the electrostatic field at this point, we can consider it constant here. What about the electrostatic field at this point? This is clearly not the same as here. For example, to first approximation, we can, if we assume that this distance is delta x, so this point is x, and this is x plus delta x, so we want to evaluate our electrostatic field E at point x plus dx, okay, delta x or dx if we make it smaller. So this can be, for example, Taylor expand by means of Taylor series, and so we're going to obtain the field E at point x, which is this point here, and to take into account for this variation, we need to add 1 factorial, of course, times the derivative, the total derivative in this case, there is only one variable, with respect to x of E x of E, I apologize, of E evaluated at point x, okay, which is this point here. Actually, let's make it better. So let's say that this point here, let's call this one x naught, and this is x naught plus dx. So in fact, we are doing x naught plus dx. This is x naught. This is this derivative evaluated at point x. This means evaluated at point x equal x naught. Okay, and this we need to multiply times dx. So forgetting about higher order terms, that's one way to compute this difference in the electrostatic field. All right. So now it gets a little bit more complicated, and what I'm about to say is very important if you want, for example, to prove the divergence or the curl theorems, okay, THS is theorems. So if you want to prove these theorems, okay, divergence or curl, also known as Gauss-Ostrogassky's theorem and Stokes' theorem, okay? So if you want to prove them, for example, you can look at Feynman or my notes. So the way you need to do it there, you need to understand, to master the following concept. So let's try to understand this concept in an easy fashion, okay? So for example, let's suppose that we have a Cartesian coordinate system in 3D, where these are the axes in 3D. So let's go here, and here, okay. This is the x-axis, this is y, xy, this is z, all right, this is the origin. So now let's suppose that there is somewhere in space a charge distribution, whatever that is, omega with a rho, which generates some electrostatic field. So the electrostatic field generated by this quantity, let's say that is a very complicated structure. So it has 3 components. It has an EX component, which can be function of x, y, and z, plus it has a y component, which is function of x, y, and z. And finally, it has also a z component, which is also a function of x, y, and z. Okay, so that's what we get. Very generic. So this is the origin of this coordinate system. So suppose that now we want to consider an infinitesimal cube somewhere. Let's sketch it as follows. So let's say that this is one face of this infinitesimal cube. Okay, and then let's do in yellow here on the back. Let's do actually the other side. Let's do it in this orange. So on the back side, so here we have some distance. Let's do this in yellow. I want to go, let's say, all the way here. So there is this distance. And there is this distance here. Okay, so then also up here, go like this, like this, all right, and like this. Now let me sketch the different color of the face on the back, so we can clearly identify the two faces. So we have the blue face here, so the blue face, okay, and the yellow face on the back. All right, great. And let's say that the dimensions of this object are, this is long so this is the x, this is the y, and this one is the height is the z. And let's say, for example, that this point here, this point is x naught, so this is x naught plus dx, and I think we can stop there. All right, so suppose that in this case we want to compute now. So let's go here. We want to compute in this region the following. So we have this E field. Let's pick only, for example, the y component of the field, which is function of x, y, and z. Let's assume that, for example, on the yellow face, on the back here, we have this vector EY. And again, this vector resides on the yellow face here on the back side, okay? So this EY, obviously, is function of, in terms of x, we are at x naught, and we can keep y and z running, variables, all right. So in this case, we can assume that this quantity is constant, so this can be constant on the face, on the yz plane, that is on this orange face, exactly the same fashion as we have done in 1D here. But what happens if I want to compute this field EY now at the blue face? So if I want to move to a point on the blue face, well, in that case, we need to do a little bit more complicated Taylor series, because we need to deal with the fact that we have a EY, which is function of x, y, z. And so we are moving, keeping running variables y and z, we are moving x from x naught to x naught plus dz. So eventually, similar to this, it will be more complicated because we are dealing with the EY, and yet we are moving along x. So we go from x naught to x naught plus dx, and we keep y and z as running variables. So in this case, this can be approximated by means of Taylor series again as EY. So don't get confused by the fact that we have EY, and we are looking at x, the expansion along x. So at x naught plus, in this case, the partial derivative with respect to x, because EY is function of x, y, and z. So with respect to x of E of running variable x, y, z, so these two don't count, so we only want to do it at x equal x naught and multiply times the x. So this is our Taylor series that allows us to find what is this EY, which we consider constant on this blue face, on this yellow face. Now the blue face changes a little bit by this correction, and now we can consider it again to be constant on the blue face if we want to here. And that's the whole essence that you need to know. You need to understand this concept to prove the divergence curve theorem, as for example Feynman does it, or as I do in my notes. So the whole point of this video was to show you, to give you a sense of how to use Taylor series to deal with infinitesimal movements in space, for example, for the electric field, and also when you can assume that something is constant and when you need to change the value of the electric field according to all these concepts. That's it.